All right, welcome back to TEWA 1 Advanced Data Analysis, and today it is the 10th lecture already, and we will be focusing on hierarchical models. But first of all, let's think about what we have covered the last week and the week before. So quite importantly, we have an overview. So that the task that we have been working on is always like this. So we have a simple choice task whereby the participants are presented by two choice options. In this case, one blue and one yellow. And then the participants, they make a choice between the two options. And after making the choice, they will see the outcome. So in this case, either a win or a loss. And in this particular case, the person chose blue, and then the outcome is a win. And what we are going to do is that we want to model it, right? So in this, under the simple reinforcement learning framework that we introduced, the model part, we will use the Riesler-Wagner value update rule. So if you recall, the idea is that the Riesler-Wagner value updates is to learn from feedback, or in other words, it is a feedback-driven learning. So how does the feedback facilitate learning? It is always that the participants, they have some expectation of the value of the choice option, and then they receive the actual feedback, and then can compare the actual feedback and their expectation. And then the difference between these two is called a reward prediction error. In this case here, the PE is calculated by using the R, the reward or outcome, minus the previous expectation. And then the prediction error here, this term is then multiplied with a free parameter learning rate, and this one is used to update the value. Note that the value update only applies to the chosen option, because only if you choose it, you will see the outcome. If you do not choose it, there is no outcome related, right? And after the value is updated, the model will also assume that person will make a selection according to the value. So the value will then be translated to action probability. And we spent quite some time last week in discussing the shape, so how the curve looks like of the choice rule. So if you recall that we have on the x-axis the value difference, value diff. And then on the y-axis, we have the probability of choosing A. If this is value difference between A and B, this is the P of A, right? So the shape is more or less like this. So this is called the sigmoid function in this case, or softmax. And then the mathematical term is like this, it's determined here. And then there's only one free parameter, in this case, tau, that is governing or controlling the slope or the steepness of the curve. So if the tau is high, then this curve is much more steep. And then if this tau is low, then this curve is much more shallow. And in this case, you can expect something like this. Doesn't so nice, but yeah. So less steep, okay? Good. And after explaining all of the components of the model, the value update and the choice action selection, so we just went to the implementation, because understanding the concept is not so demanding. It's actually quite straightforward. But what we want to do in reality is that we want to do model fitting in R, and in our case, in the Stan language, right? So then we went on to the implementation of the simple Riesler-Wagner model. And before we jumped to Stan, we also looked at the graphical illustration or the graphical representation of the model. So here, just as a reminder, if you forgot, so we have the nose, so each of the shape, the nose. If it is square, then it means discrete variable, integers. If it is circle, that means continuous variable. If there is a color inside, that means the variable is known. In this case, we know the reward, the outcome, we know the choice made by the participants. And if there's no color, that means it's unknown. So we do not know the parameter learning rates and the tau, and we do not know the internal variable value and the translated choice probability. We do not know them. And what is also quite important is that we ask the participants to repeatedly make the trials in this case. If there are 100 trials, then the value update will happen 100 times, so that the value updates from the beginning until the very last trial. So here this square, outer square, just means the number of trials, okay? And then the actual implementation is not really so important, but we moved on to the next topic, which is about so fitting multiple participants. Because if we run experiment, we do not recruit only one person, we ask multiple participants to come into the lab. And there are traditionally two ways to fit the model to the data from multiple participants. So the first one is that if you see this red square, so you will see that it is assuming all of the participants, they have the same parameter. In this case, you see the parameter here, and then here they are outside the subject loop. So basically all of them, they have the identical learning rates, they have the identical tau parameter. And you could imagine, well, this is not realistic because people are different and they might learn the task quite differently. So the next approach is usually to fit them independently. So if you see here, there's the circle, the same, this is the subject circle, but it is much larger in the sense that it also includes the two parameters inside of the subject loop. So if you see this index here, that basically means each person, they have their own learning rates. Each person, they have their own tau parameter, okay? And then the implementation is also not quite important here because we will skip it. Also, we don't do it. Good. As you could also imagine, this might also not be ideal. It is because, well, because the participants, they do have some similarity. If they are like healthy psychology students, age maybe 18, 20, between 18 and 25, they have some similarity. They are quite likely they are from the general same population, right? If this approach doesn't assume this, because this approach just assumes each person, they are unrelated to one another. So they are all independent. So this is the drawback or the challenge of this approach, okay? So to overcome this approach, then we will do hierarchical fitting. So hierarchical in this sense means there are two levels or actually multiple levels. In this case, we are talking about two levels or hierarchies. So the top level hierarchy or the level is the population level. That assumes the general population that we're interested in. In this case, healthy young psychology or university students, doesn't have to be psychology. And this is the first level. The second level is all the individuals, okay? The first level is group, so the general healthy young population, and the individual level is all of the exact person that we recruited from their home to the lab, okay? Good. And then let's just focus on the hierarchical fitting idea and then to see how that works conceptually. And then we will also look at how this can be implemented in our workflow in STEM and in R. Good. So first of all, I would like to introduce some of the motivations that we do hierarchical fitting. The very first motivation is that I already explained to you, because the hierarchical structure being group level and individual level, it is by nature the way it is, right? Because we are recruiting these people, and then it is guaranteed more or less that they are from the same population. But if we consider all of them independently, this basically overlooks this structure, which is not great and ideal. This is a conceptual motivation. And there's a second motivation, which is about the reliability of the parameter fitting. So reliability means if we do some model fitting and we get some results, if it is not reliable, then that means it is wrong, and then we cannot use it. Only when the result is reliable, we can go forward to make some inference, for instance, right? So here I will basically explain this reliability part. So suppose that I run a simulation study. Simulation basically means I know the ground truth and I use the ground truth to generate fake data. It's generated or simulated, or in other words, fake data, okay? So in this particular case, it doesn't matter the y-axis, doesn't matter the meaning. So here, this black circle is the simulated fake data, okay? And let's say we simulate the fake data for 30 participants or 30 individuals. And as long as we have the fake data, we can fit the model to the data. Even though it's fake, but the model doesn't know it's real or fake, it can just do the model fitting as usual. And we do the model fitting by two approaches. First is the standard maximum likelihood parameter estimation, whereby each person is fitted independently or individually. And then the second approach is the hierarchical approach, where it assumes the two levels, population level and individual level. So what you can compare is that how deviate or how close is the parameter fitting results from the two approaches relative to the true value. So ideally, we would expect that the estimated parameter result will just basically follow the shape of the true value, the black circle, right? But this isn't the case for maximum likelihood parameter estimation, because if you see here, this method resulted in a result of this triangle in this case, which is quite far away from the true value. And then if you see here, this is the true value, and then underlying the orange square, orange triangle, they are quite far away from the true value. Okay, also here. On the other hand, if you look at the parameter fitting results from the hierarchical fitting methods, you see that overall, perhaps it doesn't really fit so optimally to every single point generated by the fake, generated from the fake data here. Also, there are some discrepancies, especially here, there's some mismatch. But overall, if you see here, especially the second part, the hierarchical fitting approach is way better relative to the maximum likelihood approach. And it's quite fits closely to the fake data, okay? So this graph essentially demonstrates that the hierarchical result is really much more reliable. It can reflect the truth, okay? And you might wonder, well, this is simulated fake data. That means I know the data, I do the fitting. I can compare if the result is close to the truth or not. But in reality, nobody knows the truth, right? How does it fit in this case? Well, you can still imagine that there is some kind of truth, which we don't know, but it's there. And you could basically believe that the hierarchical fitting will be much closer to the truth relative to the maximum likelihood fitting in general, okay? In other words, in most of the cases that I've seen in the literature, the hierarchical fitting is really better than the maximum likelihood fitting. Great. And to give you a little bit more taste of the hierarchical fitting, so what I can show you is that I said there are two levels, but usually if you see the literature, that the hierarchical fitting, it has multiple names, terminologies. So some call the hierarchical fitting the multi-level fitting, so the multi-level modeling, or mixed modeling, hierarchical fitting, is everything they're the same. And if you are really interested in how this hierarchical fitting is related to the terminology of the fixed model and the random model, in this case, the mixed model, you can see here. So essentially, if we understand the previous terminology that I mentioned, group level and individual level, so we could imagine that the group level means everyone more or less follows the same group distribution. Suppose there is a group distribution. So this is the same for all the people. But at the individual level, the lower level, they could have some individual differences. Everyone might be if there's one person and then the second person might be a little bit higher than the first or maybe a little bit lower than the person. There are some variation at the lower level. And then these two terminology, group level and individual level, these two names, it maps to two other names. So namely fixed effects and the random effects. So the fixed effect basically means the group level. So here that means everyone is more or less the same. There's something on average. This is the fixed effect. And the lower level is the random effect. Random means some people, there is some random variation across the individuals at the lower level, okay? So fixed effects basically means the group level. The random effect is more or less as the individual level, okay? Upper level, lower level, group level, individual level, fixed effect, random effect. So this kind of terminology. So because this is quite often seen in the literature, I would like to just tell you at the beginning that they basically mean the same thing so that you are not get confused. You do not get confused by the names. If you see people, they call it a little bit differently. All right. And let's again talk about the hierarchical idea quite conceptually. So suppose that there is a population. Let's say here there's some population. We cannot measure the data from all of the individuals in the population. What we do instead is we draw random samples from the distribution. And if we draw a reasonably enough number of individuals, draw the samples from the distribution, from the population, and we could imagine that this sample will be a good approximation to the population, right? I guess this is something that we learn from statistics. So we draw a random sample and then the sample represents or resembles the population. So far, so good. So let's say all of the red dots, they are the individual samples drawn from a common population. So if we want to fit all of the individuals according to the previous two approaches that I mentioned, the first one is all of the people, they share the same parameter. So then in this case, all of the individuals, they are fitted as if this is one person, okay? And then there's the second approach. Second approach means the fitting applies to all of the individuals all independently, assuming no common structure underlying it. Okay, so this is the second one. And as I mentioned already a few times, both of them, they are a little bit problematic. So the first one is quite biased because the data is considered as it's from one person, which is unrealistic. And then the second one is sparse because there is indeed a common structure where it is not considered in this independent fitting. So it's quite sparse. Solution is simply to combine these two, right? Group level, individual level, random effect, and fixed effect to combine the two levels altogether. So the solution is to superimpose the group level distribution on top of it. Say here, this is the assumed group level distribution where all of the samples, they are drawn from it, okay? And then if we do this way, both the group level distribution, both the group level parameter and the individual level parameter can be considered or simultaneously into the model fitting. Okay. So actually, if you are interested in the model fitting, the implementation part, the change in the code is not much, but the concept is quite important. Previously, there is only the individual level, for example, if we fit all of them independently. But what we are doing right now is that we include the higher level group distribution, which we assume that the individuals, they are drawn from the group distribution. And we do this two-level model estimation all together, all at the same time. Okay. And then the shrinkage effect is something that we get automatically. So if you see here, I do this, I guess you can more or less see that from your screen, especially here, this dot, you can see that, oops. right? Yeah. So if we do this model fitting, so the outliers can also be regulated by the group distribution, which is also quite good. Because traditionally, if there are some data analysis, if we see someone is quite deviating from the others, we say, well, this is outlier. But actually, it might be the truth that this person also exists in the population according to a normal distribution. So if we do a model fitting using the hierarchical approach, so the outliers is not so problematic at all because it will also be regulated towards the mean. So this is the mean of the shrinkage effect. All right. So some more illustrations of the hierarchical feature. So conceptually, I guess you understand. So this is the basic concept. That's it. There is some individual data. There is a common group level distribution, 2 levels, group level, individual level. And another way to illustrate the hierarchical structure is like this, because we are talking about parameter fitting, right? We have to assume some parameters. So the rough idea is like this. Let me get a pen. Yeah. Wait. Yeah, good. So let's say this line, they are the individual parameters. This line, they are the individual data, okay? So we can imagine that the Y1 here means the choice and the outcome of the participants. So we are talking about the same experiments. The 2 choice, make a choice, see the outcome. So we are talking about the same experiments. The data basically means the outcome and the choice from the participants, okay? So this is the Y1. So this is Y2, for example, then that's the choice and the corresponding outcome of the second person, so on and so forth, okay? That's the data part, the known part. And then here, this is the unknown part. So theta 1 is a generic form, but basically in our case, that could represent the combination of the learning rates and the tau, the parameter, the 2 parameters. So this is the parameter from the first person, and if this is the second, then that's the parameter of the second person, and so on and so forth until the end, until the last participants. Okay. So if we do model fitting or independently, namely each person, they have their own parameters without considering the common structure, then we are doing this, right? So we only use the data to see how the parameters looks like, the posterior distribution, okay? If we are doing hierarchical fitting instead, we will have a different level, the second level, the group level on top of it. So in this case, this is the group level distribution or the group level parameter. And also we assume a normal distribution. And the reason why we assume a normal distribution is that this is widely used and it's basically follow the central limit theory. Okay, good. So a little bit technical, but not too much because there's no equations. A little bit technical part, technical consideration. So if we are fitting these participants, we will use the data from this person to inform the parameter, right? We fit the model to data, we get the posterior parameter from that person. So this is what we do. Then we have the higher level structure here. So this fitted information from this data will then be transmitted to the top level. And in this case, we can imagine that top level distribution are informed, that the top level distribution is informed by this person. And then this informed parameter information will also guide the parameter estimate for a different person. Okay, this one. So that this parameter information has 2 pieces. Input, one is from the top level group, the other is from the corresponding observation, the data. Okay. So what we see in the literature is that if some person is describing hierarchical model fitting in their paper, they will say that, well, we are considering the hierarchical fitting because it reflects the structure, the hierarchical structure of the participants, for one. For two, it is more reliable because of the reason I showed you. And they will also explain a little bit more details. Basically, they will say the hierarchical fitting allows the parameter to be more mutually informative at both the group level and the individual level. So here the arrows basically means the mutual information transmission that I showed to you. Mutual here just means this goes to there, but this also goes back. Okay, so the mutual information exchange. And what I showed you here, the illustration is maybe a little misleading. So what I said is this information goes here, and then this goes here, and then this also goes here. This is what I showed you. But in reality, this is not exactly the case, because in reality, all of the arrows, this one, this one, this one, this one, this one, everything, they happen all at the same time. Okay, good. And if you see here, the change on the graphic, on the figure is that now the big phi, so this big phi becomes a mu phi and a sigma phi, because we are assuming a normal distribution. So all of the individual parameters, they follow a normal distribution. And recall, well, for a normal distribution is straightforward. There is a mean parameter, the mu, and then there is a sigma parameter, the standard deviation. And all of the individuals, they follow this distribution, okay? Good. And some more graphical illustrations. So this is the one we see, and this one I will tell you later. And we can have a different graphical illustration. So all of here, the one below, they are the individual level distributions, and all of them, they follow the group distribution, normal. And the second one, so the individual ones, some of them, sometimes, not all of them, they are symmetrical. So maybe at the individual level, they can be a little bit shifted a little bit. So if you look at here, 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 and here, these 5 distributions, they can have their own individual variation, but their mean in this case, these colored dots, they more or less follows the normal distribution governed by the mu and sigma parameters. Okay, good. And then there's another graphical illustration. So here, everything, they are the same. So top level, and the individual level. Okay, here up to here, they are the same. What is this guy? What is this guy, right? What are they? Well, because we are doing Bayesian parameter estimation, what we need priors, right? So here, this is the prior distribution for the mu, and then this is the prior distribution for the individual, for the group level standard deviation parameter. So the prior for the mu, and then the prior for the sigma, okay? And then if you understand the graphics, I can go a little bit into this equation. So what is this? This is essentially a Bayes equation. If you see like the vertical bar, the conditional probability. What we had before is that we have the P of theta given data posterior, right? And then this one is first the likelihood and the prior, yeah, divided by the normalization. Oops. Okay, yeah, divided by normalization. So this is the Bayes theorem that we know it already. And what is slightly different is that there is one additional term variable. This is called the capital phi. So the capital phi means the group level distribution. If you simply take out the phi here and here, then this equation becomes entirely identical to the one that we are already very familiar with, okay? But we cannot take out this phi because we are doing the hierarchical fitting. Good. And what it implies is that we are interested in the posterior distribution, not only at the individual level, we are also interested in the population level parameter. So if we have some data and we have some model, we want to know, given the data, what is the posterior results of both the group level parameters and the individual level parameters, okay? And if we know this formation and we can reverse it, and then it becomes this one, this part. Good. What is quite interesting is this one. So how to better understand this part? So we know this. So first of all, this one is basically getting rid of the denominator. This is only the numerator. So first of all, we have the P here, the D given the theta. What is that? That is the same as this one, right? The likelihood at the individual level. So remember that here, this theta means individual level parameter, and here this D means individual data, because we don't have group data. We only have data from each individual person. So we have the individual data. So this is the likelihood. All right, good, very good. We know it. So what is this? So this one is the probability of the individual level given the group level. Okay, I guess that makes sense because we have something from the group and then the individuals, they follow the group. So basically this part, okay? This part is that. The individual given the group, okay? Makes sense. The very last part, the P of big phi. So that is this part, the prior of the group level distribution, okay? So maybe I've mentioned this one early on. So whenever we are reading this a chain of conditional probabilities, it's always recommended to read it from the very right hand side, the rightmost, because usually the rightmost part is the simplest. So the rightmost, and then it becomes much more complex at the left end. So here, let's say we start with the group level prior. So the prior of the group level distribution without knowing the data. Great. This can be considered as individual level prior. As long as we know the group level prior, and given the group level prior, we specify the individual level prior using a normal distribution. It's not reflected here, but we are assuming a normal distribution. And when we have the individual level information, then here, after considering the data, this is the likelihood. Okay, so if I explain this way, I guess from here and then here and then here, it is much clearer, I guess, to understand. Good. And in practice, is this one important? Well, I would say, yes, if you know it is better, but if you don't know it, this is totally fine, because this graph, I guess, is more important to memorize. Okay. Good. All right, I should stop for a sec. Any questions regarding this quite conceptual introduction of the hierarchical model? Maybe let me summarize first. So we fit model to the data, right? And we are considering the individuals. They are from a common group. So here, individual 1, 2, 3, they are from a group. So when we are considering the group level, then that is a hierarchical fitting. And additionally, because we are doing Bayesian parameter fitting, we need priors, which is reflected at the top, This is the prior, okay? G group, yeah, okay. One sentence summary. If we are doing hierarchical parameter fitting, we are considering group level distribution and individual level distribution simultaneously. So that's it. This is hierarchical fitting. Some questions. So no prior for the random effect parameters. Well, so if you are considering the variation, right? The variation among these three guys, the variation among these three guys. So then the prior is governed by this. Does that make sense? Because the individuals, they are from here, this distribution, and this sigma, the prior is determined by this. Yeah. Or in other words, if you want to map it to the concept of random effect and fixed effect, so this is the prior of the fixed effect, and this is the prior of the random effect. Yeah, now that can be linked. Any more questions? So conceptually, what does that mean to us? So hierarchical fitting, through the explanation that I gave from the last 10, 15 minutes, I think that makes quite a lot of sense, right? Because we are running experiments and then they are from quite a general population. And it seems that everyone should do hierarchical fitting, even though it is not the case always, but it seems this is quite reasonable, right? This explanation at the conceptual level, that just makes sense. So conceptually it is quite as straightforward as this that I delivered to you. Practically, that means I'm not sure what the other people will say, but what I consider is that it is always recommended to do hierarchical fitting. Consider both the group level and the individual level. And this is also less sensitive to outliers, to the bias, to someone who is a little bit deviating the group. Because if you remember the graph that I showed you, there is the shrinkage effect, and the outlier will be regulated by the group. So it's not so extreme as it was and is supposed to be if we do not consider the hierarchical structure. Okay. Any more questions? All right, okay, let's move on. So what do we have? The structure is quite generic, and this is not so specific to any single model. So we can do this kind of fitting even for a coin toss example. So for example, we have 10 coins, and we are assuming that the coins are minted from the same factory. So they have some commonality, right? So we toss the coin 100 times, and we receive some number of head, and coin number 2, toss and catch, we could receive some number of head, and then coin number 3, coin number 4, coin number 5. We could also do this hierarchically. There is a hierarchical group level distribution governing all of the commonality of the coins because they are from the same factory. And then at the individual level, they are the coin observations, head observations. We could also do this kind of fitting for regression models. So this is then something that you might be familiar with, the linear mixed effects model, which is essentially a regression. which also considers the group level distribution and individual level distribution, random effect, fixed effect for linear regressions, okay? And in our case, we are considering or applying this hierarchical structure for a cognitive model, which is the slide I will show you on the next, for our simple Riskler-Wagner model. So here, this is the previous graphic illustration where we fit all of the individuals independently. So now let's assume if we would like to fit it hierarchically with the group level distributions for the two parameters. One is the learning rate, the other one is the tau. So what would you do? So think about it. So we have here, if we have 10 people, we have 10 alpha here. I means 1 to 10. And we have 10 tau here. So tau 1 to tau 10, okay? They are independent as for now. But if we want to do it hierarchically, recall that we want to do it assuming a normal distribution. Now what would you do? Isn't it the case that we want to have a group level distribution for the learning rate parameter and a group level parameter distribution for the tau, right? Group level, normal. And what do we need for a normal distribution? So we need the position parameter, so the mu of the normal distribution, and the scale parameter, the standard deviation of the normal distribution. All right, so if you understand that part, then what we need is only two extra parameters, mu alpha, sigma alpha for the learning rates, and two other extra parameters, mu tau and sigma tau for the tau parameter. Okay, does that make sense? I guess it should, right? Makes sense. And then in this case, we will have a hierarchical model quite completed for the simple Riskler-Wagner value update. Okay, good. So if we get here and if we understand the hierarchical structure, which is quite straightforward, honestly, we just add a group level parameter, mu and tau, to each parameter that we are interested in. And so before we move on, we just have to take one step back to have a review of what we have done from a single participant to multiple participants. So here, this is the graphic illustration of the model of one single person. So only one alpha and one tau, there's no subject loop, no subject repetition. And as said, traditionally, there are two ways to feed models of data when there are multiple participants. One is that assuming the same identical parameter for all of the participants. This is not great. And we have the second way, which we feed the parameters all independently, which is also not great because it's too sparse, didn't consider the commonality of the group. So what we do is that we have a hierarchical structure. We are adding two extra parameters for this parameter alpha and two extra parameters for the tau parameter. Okay, so even though you see the complexity goes from the left end to the right end, you could see quite clearly that all of this part, right, this part, they are the same. They are the same across all of them. And what is the part that I draw? So here in this one, this is the Riskler-Wagner value updates. So the Riskler-Wagner value update part, it is always there and it is always the same. It is identical across all of these four illustrations. So here what I say is the cognitive model, in this case Riskler-Wagner per se, it is the same and identical. What is different? So the difference across all of the four illustrations is that the model is does not differ across them. So the difference across all of the four illustrations is the way of parameter fitting, especially these three, because here only one person. So across these three illustrations, the difference is how we fit it, how we specify the hierarchical structure. You could imagine this one and this one. There is also a hierarchical structure, but quite extreme. So here the hierarchical structure basically doesn't assume a variation, individual variation, so that everyone, they have the same parameters, right? This one is another extreme that basically means everyone's different. There's no commonality. And what we want to do is we just make a compromise. We combine the individual level and the group level. So how the parameter is fitted is different across the three illustrations. But the actual model itself, the cognitive model, can be the Hierarchical, can be something else. There's no change. Okay. Good. Any questions up to here? All right. If not, then let's see the implementation, because in the end, we want to do it in our standard language. Again, this is the graphic illustration, the same as before. And here, that's the formalization of it, the equations, if you may. What I said 1 second ago is that the cognitive model per se is always identical. That means these two lines here, they reflect the Riesler-Wagner value updates with the softmax choice rule. This is identical as before. Great. And what are these things? And these things, they are a little bit tricky. So let me explain quite slowly. So we can look at here, this one. So the mu of alpha is the prior distribution of, well, let's say here there's a normal distribution for the learning rates. We have the mu, we have the sigma, okay? And here, this is the prior of the mu parameter. This one is the prior of the sigma parameter, okay? Good. Similarly, we have the mu prior for the tau and the sigma prior for the tau, okay? And then these two, what are they? So here you see there's a small subscript index. So I, so here that means individual parameters. If we have 10 people, as I mentioned, here this I basically means 1 to 10, alpha 1, alpha 2, alpha 3, until alpha 10. So all of the individual level alpha parameter, they follow a normal distribution, as I mentioned, yeah, normal distribution, great. And with the mu, the corresponding mu, and the sigma, okay, the corresponding sigma, governed by their priors here and here, okay, good. And you might see something that you haven't seen before. So this and this, so what is that? So here, this kind of T is not the same as this, even though that looks quite similar, but this one means a truncate or truncation. So what that means, because we know that the normal distribution, in theory, it basically goes from infinity negative to positive infinity, right? There is no range of a normal distribution by definition. We know that. But is that something that we wanted? Not always, because for this learning rate parameter, if we know the definition, it is a parameter that is above 0 at the same time smaller than 1, okay? So you see here, there's a mismatch. How do we do this? Well, we go to the x-axis and then we find out where is 0, where is 1. And we, should be here. And then we draw a line and then we only take the parameter density in between the two ends. So this is called truncation. We just cut it according to the range that we specify, okay? And then we do the same for the tau parameter in this case, because we know we presume that it is between 0 and 3. Then we give the truncation 0 and 3. Okay. Good. This is the truncate. And you might imagine, if you are curious, well, we know there's something which doesn't have a range, but we just arbitrarily give a cutoff, 0, 1, 0, 3. Will that cause problem? Indeed, yes, this is quite problematic in hierarchical fitting. So that will be motivating the next session. So the next session will be about optimizing and make your Stan script much more efficient and no error, okay? But for this educational purpose, I show you now this not ideal solution, and then later I show you how to improve it. So this problematic implementation, even though problematic, but it's quite easy to understand, right? Good. So graphically, if you are interested in to hear more about that. So graphically, let's say we have the normal distribution, 0, 1 group, okay? Oops. And we have the individual level normal distributions, okay? So all of them, they will be truncated. 0, 1, same. And then they follow this. And you see here, there are many more truncations around, which is not ideal. In fact, quite problematic. So we will find a way to get rid of it in the next session. Good, good. All right, so a simpler question to you, and you can write it in the chat. So assume that we have a simple Ritzler-Wagner model where we have 2 parameters per person, alpha, tau, right? 2 parameters. Assume that we have now recruited data from 20 participants. So could you please tell me how many parameters are there in total if we are fitting the model hierarchically? So let me repeat the question. We know a model. If we have 1 person, everyone has 2. And now we have 20 people, but we are fitting it hierarchically. So how many parameters are there? And you can write it in the chat, and or you tell me by unmute yourself. Both should be fine. Okay, there are a few options now. So 41, 42, 42, 44. Okay, so any more comments? All right, so let's see. Yeah, you're right, 44. Yes, exactly. So we have 20 people, right? So we know we have alpha, we have tau, okay? So that means we have 20 this, 20 that. This is 40, no surprise. Good. And we have a mu here and sigma for the alpha, and we have a mu and sigma for the tau. So here 2, here 2. Altogether, we have 44. Does that make sense? This might be the question for the exam. Might be, I'm not sure, no guarantee. So in the exam, maybe I change it to 30, and then you can do the new calculation. All right, that makes sense? Yeah, okay, great. Perfect. And then here is the implementation. But again, don't really worry too much because of the truncation, this implementation isn't really working very well, so we can skip. All right. Maybe I can show you something. It's not here. Yeah, I think I will skip because the next session is more important. So because we want to do this optimization, we want to get rid of the truncation, which causes a lot of problems. But before that, any more questions, comments? Everything's okay? Yeah, there's a question in the chat. So can you compare the model performance between mixed effect models and fixed effect models? Does that make sense? Yeah, let's go to this graph. So you are saying that does it make sense to compare these three, right? Essentially. Yes and no. So what is the philosophy of model comparison? So the model comparison, if I put it in a very simplified description, so we have some data. The data is always the same. So we have, let's say 20 people in this case from the last example. We have 20 participants. We have 20 set of choices, outcome from the 20 people. So the data is always the same. And we want to explain the data. We want to explain what might be going on in their mind by proposing or developing cognitive models, right? This is the idea. And we have model 1, 2, 3, for example, 1, 2, 3. Okay. And in essence, what we want to do is that, so all of the models, they differ a little bit. So one can be Risk-Wagner, the other one can be Risk-Wagner with a dynamic learning rate. Then the third one can be Risk-Wagner with a dynamic top parameter. Well, they are that different. And we compare to see which one's better, which one's worse. And we focus on the better one and we go forward. This is the idea. And so what the question in the chat about is that we can also fit each of the model differently. So for the model 1, we can fit, well, let's number 8. This is A. This is method B. This is number C. So we can fit this model with 2 methods. We can fit the second model also with the 3 methods. We can also fit the third model with the 3 methods, right? So you see here is quite extensive and maybe it's too busy. And we have to fit 9 models and then compare. It is a lot of work. Okay, good. So to answer the question directly, does it make sense? Usually, yes. So you can do that. And because the data is always the same. This is always the same. So from a quite mathematical perspective view, if we are doing model comparison, as long as the data is identical and we fit models, either the model is different or the way to fit the model is different, they are considered different models. But the data is always the same. So as long as this condition is met, the data is the same, so then we can compare, okay? This is like from the quite mathematical perspective view, in the sense that we don't care about the cognition and then the hierarchical structure. But in reality, does that make sense? Usually no. So because from nearly 90% of the work that I see, if the work is considering 2 methods, individual fit and the hierarchical fit, the hierarchical fit is always better. So what that means, in essence, if you say, well, B here means the individual fit, C here means hierarchical fit, we can compare M1, B, and C. We can compare M2, B, and C. We can compare M3, B, and C, okay? It is nearly always guaranteed that this phi here will be the best for model 1. This phi here will be the best for model 2. This phi here will be the best for the model 3. Okay. And a little bit more practical consideration is if you are writing a paper, let's say you just have the simple data that we have been working on all the time. So choice data, make a choice, and then see the outcome. Let's say we really have 3 models. And we have these 9 variations. So in reality, what do you want to do? So if I were to do this task, I will really not do the 9 variations because it's too much. Usually actually not, because there's server, it runs faster, but conceptually this is too overwhelming, and I do not want to do that. So what I do in this case, if I were to do this, so I could do, let me erase something. The color. Okay, so I would first select the baseline model. So the baseline model, let's say this is simple risk Wagner without variation. And within the simple risk Wagner, we have ABC, right? That's the one we've been seeing. So we have the ABC. And within the baseline, we do the ABC. And then let's say, well, great, the hierarchical one for model 1 is the best. And there's implicit assumption that if the hierarchical fitting is the best for model 1, then the hierarchical fitting for model 2, 3, 4 will also be the best. So in this case, I will only do M2 with the hierarchical fitting and MC with the hierarchical fitting. In this case, that's the C version. So in the end, how many do I have? I have 4, right? I have M1 fitted by the methods A, B, C, 5, I think. So this one, there are 3. And then I have M2 with the 3 fitting method, and M3 with the C fitting method. So in total, I have 5 rather than 9. All right, does that make sense? Yeah, okay, cool. And then if you write a paper, you just basically describe what you have done. So we first run this with 3 different fitting methods. We found out hierarchical is great. And we apply the hierarchical fitting for all the remaining models, 2, 3, 4. And then do the normal comparison. All right, other questions? And then now that we are discussing these things, and maybe another example. So if you heard about something called a drift diffusion model, maybe it is used for fitting reaction time, okay? When there are 2 choice options. So let's say we are choosing 2 choice options. Wait, I can do this. Yeah, okay. This is a completely, well, related, but actually quite different topic. And don't worry if you don't get it, but I will just explain it to you so that if you're interested, you can go forward and look into the literature. So usually this is applied in perceptual decision-making very often. So let's say we have a field, which is a circle. There are some random dots. And some of the dots, they are moving rightwards, and some of them, they're moving rightwards, okay? And assuming that if 90% of the dots, they move to the right, and 10 move to the left, and I'm asking you, what's the direction the dots are moving? And it's quite easy that you say, well, right, okay, easy. If this is 80, maybe also easy. If 70, maybe also easy. Maybe when it is 55, and then the other one is 45, then you might see it's quite noisy because nearly half is moving right and moving left. Then it becomes quite random. And if I ask you in this case, where the dots are moving, you'll say, well, I don't know. And it might also take you longer to respond, right? And then some researchers, they come up with a model to approximate this process. And then this process is called a drift diffusion model. And it assumes this. Say I have 2 actions. I just say, I report the models are moving right or decisions, or I report the dots are moving to the left. In the beginning, before I see the dots, I'm somewhere in the middle. I say, I don't know. And I see the motions, the dot motions. And if I'm in this case, 90%, then I'm accumulating evidence. So I see, well, if this is moving right or moving to the left, I just accumulating evidence. And the way to accumulate evidence, it goes like this. It's also quite noisy, okay? Goes here, here, until the evidence is accumulated above a threshold, okay? So when the evidence accumulating part is across the threshold, then the decision is made. And the difference between the beginning until the time the decision is made is the RT simply, right? So you are seeing the stimulus, you are seeing something, deciding something, and you are just observing something and thinking something, all right, good. Accumulating evidence, and when your mind is made, when you see enough evidence from the screen is too much, and then I say, okay, right. So this is the description. And then there are some multiple parameters, and this is too much. I don't want to show you that. It's not also important, also not important. Okay, this is the general idea of the DDM, the drift diffusion model. Good. So why am I telling you this? Because there's some similarity between the task that we've seen. So we have a task where we have two choice options. One is blue, the other one is yellow, right? And then you are updating the value according to the Risk-Wagner. And then the value updating part can also be considered as a evidence accumulation. So basically this. And then there is a new trend, started not so long ago, I think 4 or 5 years ago. You can imagine is to combine the DDM together with the Risk-Wagner or the reinforcement learning in general. So in the literature, they say, well, something called RLDDM, means reinforcement learning together with the drift diffusion modeling, okay? Combining the two parts. And then now let's go to the question that we are interested in. So the question why am I talking to you about this chunk of new things is that we are talking about model comparison. So let's say we run 10 participants, okay? And we have one model, oops. We have one model 1. It only considers the RL part. And we have the second one that considers the combination between the RL and DDM, okay? Good. And then we do model comparison and we found out that this one is worse than this or better. Doesn't matter. So does that make sense? Can we do that? The question is, can we do that? So let me explain. So we have the data from 10 participants. So we have the choice data, we have the RT data from the 10 participants. And we come up with two models. For one, we only consider the RL part. And for the second, we consider the combination between RL and DDM. And we do model comparison, we find out maybe M2 is better than M1 or worse, doesn't matter. So the question is, can we really compare these two? Does the comparison make sense to conclude that one is better than the other, or just completely no sense? Yeah, think about it. Any idea? One says, yes, that makes sense because that explains the test data better. Any other? The second comment says we should be able to, so that means that makes sense, I guess, since the DDM can be considered as another variable. Okay. And other thoughts? Does anyone think it doesn't make sense to compare M1 and M2? Could there be the issue of overfitting? No. This is not the question for next week, but no. And someone says, I'm not sure if that makes sense. I think we can only compare them if they estimate the same parameters. I'm wondering if the models are a bit redundant. Okay, since M2 contains M1. Right. Okay, maybe this question is too tricky. So remember what I said a few minutes ago. I said if we want to compare the models, right? We have M1, 2, 3. We have 3 models, okay? The prerequisites so that they can be compared against each other is that they are trying to explain the same data. So this is the only prerequisite. So then think about these 2 models. If we are only considering the RL part of the data, so we are only using the choice from the participants. And then here, if we are doing RL-DDM, so what we are doing, so we do need the choice part because the RL, but we also need the RT part for the DDM, okay? So then in these 2 cases, the data is not the same between the 2 models, so that they cannot really be compared against each other. So you can't do that, essentially. So what you can do instead is, well, you have a M model, the RL part, you have a RL1 implementation, standard risk Wagner, RL2 with some variation, RL3 with some other variation. And then these 3, the RL variation together with DDM, these 3, this can be compared against each other. But for a model only considers choice versus a model considers both the choice and the RT, the data part, so here, this part, this is not the same. So in this case, they cannot be compared. And then the result you get is basically meaningless. You can't really see too much from it. So there's a question, okay? So the question is, I can still predict, I can still see if the second model, how well that predicts the choice, yeah? Yeah, so then that's really a advanced question. Thanks for the comments. So the question, the comments is regarding that even though the data part is combining choice and RT, but there is anyway a choice part. And then there's the C part. So what we do in reality is that we partition the log likelihood. This is really the next topic, but we can talk about it briefly. So when comparing models, we need some metrics with some numbers, some criteria to do model comparison. So to compare which is higher, which is lower numerically, okay? So the number that you get from model 1 is only the model evidence, let's call it that way, before we go to the topic, without using the terms supposedly from the next week. So if we are considering model 1, we are only calculating the model evidence for choice. And if we are considering here in the second place, we are calculating the model evidence from both the choice and then RT. And in most of the cases, this evidence is only not one number. And why am I saying that is advanced? Because in reality, you can just partition this so that the one number can be divided, one for the choice part, the other one for the RT part. And then if you are saying, can these 2 be compared? So model evidence for M1 versus model evidence from M2, but the partition part for choice. Yes, in this case, these 2 can be compared. In this case, yes. But for only one number, if you get a number from M2 combining both choice and RT, this one cannot be compared with M1. Does it make sense? And also, just because this went back to the original prerequisition, right? Because if we are calculating the partition, the sub component of it, then this meets the requirement. The requirement is the data is the same. In this case, because the model evidence is partitioned, then the data is the same. So if they're the same, then we could be able to compare. Okay, I guess that makes sense. Someone wonders how this partitioning can be done in code. Well, next week. Well, maybe next week we don't talk about that because this is quite advanced in a way. So we can see. Good. There's one other comment I didn't touch upon yet. So the question is, if I replicated a study and analyze the data using the MLM, can I draw any conclusion on the replication part? So the data is not the same, neither is the analysis.
Sorry, I didn't wrote it. Sorry, I just meant, for example, if the original study analyzed data using, I don't know, usual methods, data analysis methods as ANOVA or something else, and I replicate the study, but I analyze the data using multi-level modeling, hierarchical modeling. Can I then draw a conclusion whether the effect is the same or the study has been replicated or not, or the reviewer will say, no, you used another method of data analysis?
Yeah. So in a quite strict sense, you have to use the same analysis.
Even if I know that the data analysis is not the best one. So as you said, it's always better to use a hierarchical data analysis.
So if you ask me how to do this, how to write a paper, so the way I would do it is that I first really replicate exactly what has been done in the original data. And as a supplement, I say, well, because there is a method advancement, I'm also considering the multi-level fitting. And then I also show the results. And then now you are able to compare the results both from the original methods and then second from your new methods, multi-level, for instance. And if they match up, that's great, right? Because even though you use different methods, they have the same conclusion. But if they do not meet, if they do not match up, there might be something that you have to discuss.
Thank you.
Yeah, thanks. Good. Any other questions here? And all in all, so here this RLDDM part, this is quite interesting, and there are not too many. There's not too many work yet on this topic. I think less than 10 papers are about this. Maybe more nowadays, but not many. Not like 100. Okay, good. All right. We don't have much time left for the next topic, but maybe let's briefly introduce that, and then we can continue next week. Okay. So why do we optimize STAN code? It's basically like writing a paper. We write a paper, we write a manuscript, your thesis, for example, and then you write it within a month, for example, and you send it to your supervisor, your colleagues, and then they will always find some way to optimize it. to revise it. And then this is the same. So because we are implementing computational or cognitive models in STEM, just another way to write something, right? Usually the first draft is not great. And we write the first, and then we go back to see where we can improve. This is a rough idea. It doesn't have to apply to computer programs. It's everything, like working on your thesis, just writing papers, same. And there are multiple ways to do the optimization in our particular case. So there are 4 ways I'd like to introduce. I will explain them one by one. I will try to explain the first 3, and then the last one, which will take much more time. We do it next week. The first one is pre-process the data. The second one is to specify a proper model. And then the third one is to run vectorizing. And then the last one is reparameterization, okay? And for this one, we do it next week. Okay, good. So what does pre-process the data mean? If you know Stan already from the experience that I show you, from also the experience that you run it, maybe you run it from your own, you might have the feeling that Stan is the language that does MCMC, so that does the actual parameter fitting. It is not so great to do some data cleaning and data reshaping. So what I want to say is do everything as much as you can before you enter the data into Stan. Okay? So that means if you want to remove some participants, remove it in R so that it is ready to be entered into the Stan code, instead of removing that participants in Stan, which is quite tedious, honestly. It's possible you can do it, but it's not the purpose. Okay, so the purpose is to parameter estimation. Don't do data cleaning, pre-processing related stuff in Stan. Okay, so this is the pre-processing of the data. Do as much as you could outside, and then Stan only for model estimation. And then there's a comment asking, is it generally faster to run Stan code in R or Stan? I wouldn't say there is a difference. So let's say we want to do a data pre-processing either in R or Stan. It's the same, I guess. I wouldn't say there is a difference. But then you are really taking away the power that Stan is designed for parameter estimation. Yeah. And also because we could debug if you didn't do the data pre-processing correctly in R, you can debug it. But if you do it in Stan, then it's quite difficult to debug. We will see that how difficult that is. Well, how unintuitive that is. Okay. Good. So here, let's say, do as much as you could in terms of data preparation and data pre-processing before you send the data from R to Stan. So do it in R. Second is specify a proper model. Well, this is actually the most difficult part, because if you have a task and if you have no prior experience at all, so if you have the choice task, we have 2 choice options, make a choice, see the outcome. I ask you to analyze the data and report it back to me, write a paper, write a report. What do? You just basically count how often the participants are choosing the choosing the better rewarded option, right? This is actual the choice accuracy, if you call that way. That's the only thing you can do. Maybe you could also analyze the reaction time, but that's the only thing you can do if you had no idea about modeling. And then you heard about model, you just want to model it, you do it. Okay. So now basically the question or the challenge is how do you know the model? Well, this is quite challenging. So the solution usually is follow the literature to see in this particular task who the researchers, how they model it. Maybe using Risk-Wagner, maybe use something else. So look at the literature. And also ask your supervisors if you want to, if you say, well, for your master thesis, for my master thesis, let's say me, for my master thesis, I heard about something from the TEWA and I want to do a master thesis project regarding the model. Well, your supervisor must know it, right? So in this case, ask the experts. And also start from simple and then build complexity. So this idea, I guess, is quite intuitive, because if you write a paper, you do not write a paper entirely. You write maybe first the methods and then the results, right? Here is the same. You first write something a little bit simpler, the simple risk-Wagner, and then later you say, well, I want to have a dynamic learning rate. I want to have a dynamic tau parameter. Yes, that's great. Yes, you could do it. But start from the simpler one, the simplest one, and then you gradually change it to be more complex, rather than you start with the most complex model with both dynamic learning rate and a dynamic tau, which might just kill you, I think. And then there are some other suggestions, and then this we can talk about after the holidays. This is a little bit off, I think. All right. And then the third way to optimize STEM is to run vectorizing, to take the advantage of vectorization that is enabled in STEM. So vectorizing, what does that mean? If we do not, if let's say we have data from 10 coins, let's say 10 coins, head and tail. And if we want to feed the model data from the 10 coins, the very first attempt is perhaps, well, we can write a 10 loop, for loop, looping from the first one to the 10th. And then here we do some sampling statement and then we finish, okay? There's a for loop. So vectorizing basically means, well, because STEM is supporting full vectorization, we can take advantage of the vectorization so that we could get rid of the loop. Examples are shown earlier, like this. So this is like exactly the coin flipping. So if we do not consider vectorizing, we could write a for loop. It loops from first to last, but essentially all of the coins, they follow the same distribution so that you can get rid of the for loop to take the full advantage of vectorization. Okay. Another example, say this is a hierarchical model. Let's say we have 10 participants. That means we have 10 learning rates. We didn't write a for loop to specify the connection or the hierarchical structure between the individual level and group level. We didn't say for participants 1 to 10, each of them, they are following the normal distribution. We didn't do that. We just say all of them, this is a vector. The vector is following the normal distribution. So vectorization, right? Another example from the weight height example that we've seen. So for each of the individual, we have the weight data, we have the height data. And to implement the regression model, we could run it one by one person by one person, looping it from first to the last. But since we know STEM supports full vectorization, we just want to get rid of the for loop so that this is a vector, this is also a vector, okay? So recall that's vector, well, this is a vector plus a vector with the same size, it just becomes another vector, right? So vectorization. Good. So those are the first three methods to optimize your STEM code. Let's go here. The first three. So pre-process the data, run as many calculations or pre-processing as you could outside STEM, in this case in R or others. Second, specify a proper model. And then this is a little bit tricky, but look at literature, ask person who has the expertise, and starting from simple, build the complexity gradually, piece by piece. And the third one is run vectorizing. So vectorize your STEM code whenever you can. A simple heuristic is that if you are writing a for loop already, and then ask yourself, can I get rid of it? If the answer is yes, then that means you can vectorize it. If the answer is no, maybe you keep it there. Sometimes it doesn't really do this way. Sometimes you do need the for loop because the model is too tricky, or sometimes the function doesn't support vectorization. This happens. But just always ask yourself, if you see a for in the code, ask yourself, can I vectorize it? Can I get rid of it? Okay, and then do the decision accordingly based on the answer you will see for yourself. All right. And then the vectorizing is, as you could see from the slides, it can be a little bit heavy technically. So we do it the next week. Okay. Are there any questions, comments? All right, no, good.